enjoy the palm trees in the background in the meantime.
Well, the other thing, I don't know if Alexa asked you, is it okay to have questions interrupting you, or would you prefer they wait to the end?
I'm good with either. It's going to be hard for me to monitor the Zoom chat. So.
Okay, I'll keep an eye on the Zoom chat, but is somebody in the room actually projecting this onto the big screen? Looks like Kristen might be, right? Okay, great. So Kristen, if you can keep track of the room, and I'll keep track of the Zoom chat. How about that?
Yeah, sounds good to me.
Okay.
All right, then maybe let's get going. Good morning, everybody. I'm pleased to welcome Kristen Dage to give the seminar this week. She's an FRQ&D postdoctoral fellow at the McGill Space Institute. Before that, she got her PhD from Michigan State University, where she was advised by Steve Zepp. And I think you're gonna find her talk to be very cool and wonderful. So Kristen, go ahead and take it away.
Thanks. Thanks for inviting me here. I'm very excited about ultraluminous X-ray sources and globular clusters. So I do a mix. It's sort of a mashup of, both high energy astrophysics and studying black holes, as well as trying to understand the star clusters. So I'll mostly be focusing on the X-ray aspects for now, but Alexa and I have been plotting for how we can sort of further understand the globular clusters, and I'm very excited about that as well. So to sort of start out, I care very deeply about compact objects. So these can be black holes, neutron stars, or white dwarfs. I will talk a little bit about all of them. I will mostly be focusing on black holes for this talk, though, but I promise to talk about each one of them a little bit by the end. I just think they are some of the most exciting physics in the universe. There's a lot of extreme gravity here because of the high density, and they are very exciting. So one of the problems with observing black holes is that the definition of a black hole is something that is so dense that it doesn't give off light of its own. And as an observational astronomer, the techniques I use are looking for, signals, specifically electromagnetic signals from stellar objects. So this is kind of a problem. But we are able to study these both with electromagnetic and gravitational wave detectors, because fortunately for us, black holes interact with things that do give off light. So of course I have to show even though I don't work on supermassive black holes, I have to show this, beautiful EHT image of what we can do using X-rays, optical, UV, and radio. And then, something that's, new within the last decade is, the ability to detect gravitational waves. And so this is a great way for how we can measure stellar mass black holes as well. But of course, the problem is, what about intermediate mass black holes? So, very roughly, we've discovered mostly thanks to gravitational waves, things, black holes that are within 5 to 100 stellar masses. I would say a little bit between 1 and 200 of these. And we've discovered so many supermassive black holes that are 1 million to 1 billion times the mass of the sun. We have only candidates and no confirmed objects in this range, which is why I've chosen to represent it with a picture of my parrot Rufus, just because we don't have anything yet. And so I like to call these the Goldilocks of black holes. They're not too big, they're not too small. They're supposed to be important, and we have no idea how we can find them and confirm them. And for stellar mass black holes, these are, sort of at the heart of a new puzzle in astronomy, because when LIGO Virgo turned on in 2016, they found more and more stellar mass black holes than was predicted at the time. And so there's a lot of open questions about the progenitors to these, and that's something that I'll touch on in a bit more detail in a few slides. So the main way, not talking about gravitational wave detections, but the main way we observe black holes is through X-ray binaries. So this is a nice artist rendition of a typical X-ray binary. So you'll have your compact object here. It's friends with a star. And because this one is more dense, it pulls material from the star towards itself. The star is rotating, and so there's conservation of angular momentum that forms this beautiful accretion disk. which gives off signals in X-rays. Now, I am an extragalactic astronomer, which means that I do not touch things within the galaxy. And you lose a lot of detail. So a lot of the information and detail in this diagram are not things that I can observe. And so typically the main thing I care about is studying the accretion disk in X-rays. Another important thing to define is the Eddington limit. This is now about 100 years old. So Sir Arthur Eddington in the 1920s said, if you have gravity pushing inwards and radiation pressure pushing outwards, then the point where those two balance is a limit. And so what this is saying is that if you are an object of 10 solar masses, you should not be allowed to get above this X-ray luminosity. So this magic number is 10 to the 39 ergs per second. And of course, this scales with mass. So you could imagine for a supermassive black hole, it's no problem that they reach this luminosity or higher. But if there's something that we know is not a supermassive black hole that gets this bright, this is interesting. And so for some context, the X-ray output of the sun is about 10 to the 27 ergs per second. And typical galactic X-ray binaries can range from 10 to the 33 at the low end in our galaxy, and a X-ray binary that reaches 10 to the 37 ergs per second would be considered bright. So these are, 2 orders of magnitude at least more brighter than typical galactic sources. So of course, the Eddington limit is not a hard and fast rule. It's more like the Pirate's Law or a speed limit. You're not supposed to go above it, but plenty of things exceed this limit anyway, and those are the things that we are interested in. And so there's 2 explanations for how this can happen. The first, of course, is that it's simple. You just say that it's something that's more massive than 10 solar masses, and then you're sort of in this physics regime that we understand because it just scales with the mass. And maybe this is a good way to find intermediate mass black holes. And then the other scenario is that you do have something that is less than 10 solar masses, but it's not accreting under the assumptions that Eddington made when he did this calculation. So there could be other avenues to draw on material to be accreted and produce X-rays. Both of these are very exciting scenarios. So one thing to keep in mind, and this one of the nice things about stellar mass black holes is that they sort of scale from supermassive black holes, but have things that happen on much shorter timescales. And so one thing that we know happens in supermassive black holes are outflows. So we don't know what launches these yet, but winds from the star, for instance, in a stellar mass system could blow excess material around the system. And so that would be something else that could be accreted, but importantly, it serves to obscure a lot of the system. And so, of course, this is an artist representation for something I don't work on, but the general concept is the same and, important to introduce here. So in terms of observations, one of the things we know about ultraluminous X-ray sources is that a lot of them live in young star-forming regions of galaxies, and this is a very famous example of one. And so you can see that this is the optical counterpart to the ULX right here. And I think the number for these systems is about 600 at this point. And so the general consensus is that almost all ULXs are in these young star-forming regions of galaxies, and therefore there are implications about the systems that we can take from their environment. But this is not all ULXs, and so at this point about 20 have been identified in globular clusters associated with early type galaxies, which is really exciting because these are very, very different and exciting places than star-forming regions of galaxies, and it's so exciting that we have them in this old environment. And so one of the consequences of being in a globular cluster, and I like to draw the analogy between a blob of bees and a blob of stars because this is not a static image. All of these stars are moving and they're interacting with each other. And one of the consequences of being in a dynamic environment like this is you can have something called preferential mass exchange. So if you have 2 objects in a binary and a more massive object passes nearby, then one of the objects in the binary will actually be swapped out for the one that's passing by. And so this means that if we observe an X-ray binary in a globular cluster, it doesn't mean that the donor star and the compact object were born together. They may have traveled, through the cluster to meet each other. And so there's just a very different evolutionary path that it takes. So this is my visual representation to think about the two different types of ulexes. So the star-forming ulexes are kind of like my chickens, where they were born together, they're young, they've spent their whole lives together. And one of the consequences of being associated with the young system is that you could potentially have a high mass donor star. And if you have a high mass donor star, then you could have, winds launching material off. Whereas the globular cluster ulexes are a bit more like Statler and Waldorf, where they are old. They had to go through an entire Muppet, theater of Muppets to meet each other, so dynamical evolution, and they are affiliated with low mass donor stars because all of, the more massive stars that were in the cluster at some point in their lives have, blown up and died. So this is exciting because this means that we can use, knowledge of the environment to understand these really unusual X-ray binaries. Now, so sort of going back to gravitational wave sources, since we know globular clusters should be places where black holes form, one of the leading questions in astronomy for a while, probably for the past 50 years, has been where are black holes in globular clusters? Because there is a lot of theoretical work that says that they should get booted out, once the black hole forms. And now a lot of newer simulations and observations are showing that this might not be the case. I really like this result from Morsher 2013 that showed that stellar mass black holes can be retained, and the timescales on which black holes get booted out of the cluster may be longer than previously thought. And there's been a lot of work since this paper on the theory side showing that black hole binaries in globular clusters can actually explain a lot of the observed LIGO rates. So finding observational evidence of black holes in globular clusters to back up this theory is very, very important. But the problem is, of course, that black holes are hard to observe. We didn't have any observational evidence for a black hole in a globular cluster until 2007. In terms of globular clusters in our galaxy, we know of a few, maybe 7 black hole candidates in galactic globular clusters, and we have I think on the order of 2 or 3 confirmed globular clusters now. That this is some very new results, but this is still less than 10 globular clusters for our galaxy. And when you consider that there are about 150 globular clusters in our galaxy that are not indicative of the greater population of globular clusters, this is a problem, because that means that 150 globular clusters is not that much when you can turn to any other galaxy in the universe that has hundreds to thousands to tens of thousands of globular clusters around it. And so that means that if we can try to study the black hole contents of extragalactic globular clusters, that we are going to be able to get a more representative sample instead of the sample of galactic globular clusters. And so this is exactly the thing I've been focused on. So fortunately, we have a lot of telescopes at a lot of different wavelengths, and I've tried to make use of as many as I can. I'll talk, I think, about almost all of these. There's a few I'm going to focus on in particular, which are Hubble, of course, Chandra, XMM Newton, and then ground-based telescopes like SORA and Gemini. So the practical way of doing this is to use ULXs, which are sort of logical black hole candidates. And so even if you go to pretty distant galaxies, you'll still see the brightest X-ray sources, and we can cross-match these to globular clusters using Hubble telescope. So this is an image of what it looks like to actually do this. So this is a Hubble image of, I think this is my favorite galaxy, NGC 4472. So the thing that looks like the galactic globular clusters I was showing earlier, this is the host galaxy, and a lot of these little point sources here are globular clusters, and then the green regions are X-ray sources that were matched to globular clusters. So this is great because that means that we can actually use both optical and X-ray to study these systems. And something really worth emphasizing here is that extragalactic globular clusters show up as unresolved point sources. But, that's a good thing because we can do integrated light spectroscopy of the entire cluster so that, in sort of one go, we can characterize the host cluster as well. And so that means that we can get the age. We can use it to confirm the distance of the X-ray source, which is, sort of essential to calculating the X-ray luminosity. And then we can also look for the, the sort of the chemical content, the metallicity of the globular cluster, as well as search for any emission lines that could be due from the X-ray binary. So this is, one of these spectra. So this is sort of a boring globular cluster spectrum. And, anything that might look interesting is because, unfortunately, Gemini does have some defects. And so this is one cluster where we are able to, actually measure the radial velocity of the cluster to confirm that, this really is an object hosted by a cluster. But one of the really exciting things we see in some of these clusters is forbidden optical emission lines. So we have, for 2 of the clusters that we have optical spectroscopy of, we have these beautiful emission lines rising above the globular cluster. Example that has both forbidden oxygen emission lines and nitrogen emission lines. The source is kind of weird. There's been a few debates about the nature of it. And I just got a Chandra program to follow up on it that I'm hoping will shed some, more light on it, but it's a very strange system. And then, sort of a quick note about these forbidden emission lines. So I'm not an atomic physicist by any means, but there are a lot of constraints on forbidden emission by atomic physics. And essentially, there's a criterion that it requires a very low density. And so these might be really good suggestions of outflows because that is also something where you have a low density. So this is my favorite optical spectrum ever for my favorite source. And so what you're looking at here, these red and blue are Keck and Hubble spectra of the source. The black line is a model fit to the globular cluster continuum. And this basically, so what the globular cluster would look like if it didn't have this giant oxygen emission line here. And so this is the O3 emission line. So this is 5007 and 4959. There's a 3-to-1 ratio set by atomic physics. And you can see that this has a strange structure. And it's especially odd because typically when we see O3 emission lines, they're narrow. So in the case of like planetary nebulae. So this is a weird system. And so we know that it has a lot of oxygen. And because we modeled the globular cluster continuum, we can place constraints on the excess hydrogen in the system. And basically there wasn't any. And so an object that has a lot of oxygen and no hydrogen is a carbon-oxygen white dwarf. So we think this system is a black hole accreting from a white dwarf or an ultra-compact X-ray binary, which are very exciting systems. And they will typically have orbital periods of less than 1 hour. We think that this one actually has a 5-minute orbital period. So the structure and the composition of this emission line actually changes over time. So we've been, observing it almost every year starting in 2016 using SOAR, but we also have previous Gemini measurements from 2009 and 2011. And so you can see that the amount of flux in each of these wings in the core does change over time as well. So another way to view this is by looking at it this way. So this is the amount of flux in each of the those wings in the core over time. So this is the 2009 observation. And when we got to this one, this is a 2016 observation, the flux was so low that we were worried that we were just not going to be able to observe it anymore. And then sort of inexplicably, it started getting brighter. And so we have, we're still observing it. We're going to observe it in April. I observed it last March, and those emission lines are still there. I'm not sure exactly how to interpret this rise yet, but one of the valuable things that we can use this decline to do is to place constraints on the size of the oxygen nebula in the system, using the time scale of the decline and the constraints from atomic physics. And then it also helps that it's variable because that just confirms that this oxygen emission has to be associated with the X-ray binary and not, some serendipitous event happening in a system that also hosts an extremely bright X-ray source. So now going to the X-rays. So I mainly use Chandra, and I think I'll show a little bit of XMM in here. And this is what an X-ray image of these fields look like. So this is NGC 4472, again, but an X-ray. And a lot of these point sources are X-ray point sources. But if they are not associated with the globular cluster, then they could be background AGN trying to trick us. But if they're affiliated with the globular cluster, then that suggests that these are truly X-ray binaries hosted by the globular cluster. So this is what the X-ray image looks like. And so one of the beautiful things about X-ray detectors, as opposed to doing optical observations, is that if this is sort of your classical schematic of what an optical telescope looks like. So the light comes in, gets bounced off the mirror, focused, and sent out to the CCD. So if I wanted to know the position of something on the sky, I would take a snapshot. If I wanted to know the variability of the source over time, I would take a series of snapshots. And if I wanted to do spectroscopy, then I would, have to put in the grading, put in the slit, align the object in the slit, and then take a spectrum. X-ray telescopes do all three of those in one for free. So as the X-ray photons come in, they get bounced through these mirrors and then reflected into the CCD. And so it tracks, and especially to Chandra, with a high degree of accuracy, where the photons came in, the relative timing of the photons, and also the energy of the photons. So because we can track the relative arrival times of the photons, that means that we can actually look at their X-ray light curves. So the number of photons coming in over time. So both over the course of observation or over the course of many observations, if that data exists. And so this isn't clear, this doesn't necessarily have like one physical cause to interpret yet, but it's still useful because a source that is sort of flat over time like this is going to fundamentally be a different beast than something like this, where it goes up and then it goes down, and it's very exciting. So here are some example of sources that show variability within an observation. So on the time scale of hours, typically. There's this source, which drops by like several orders of magnitude over about 4.5 hours. And then this source also shows similar variability. And then they can have combinations of variability, like this source is doing something very strange here. And then we also can keep track of their long-term information. So this is a source where we're still observing it with Chandra. This source was observed both in the 90s by Rosat and then in some early Chandra observations. And then we have just not detected an X-ray since 2003, which I'm personally very sad about. And a lot of the other sources just do not vary within an observation. And so this is really exciting because 20 sources is not a large sample. These are, like the way they were selected is that we looked for things that are unusually bright in X-rays and hosted by globular clusters. So even with that small sample, they are not all the same. So that suggests we have, a mix of different physics going on here, accretion physics happening, or like a mix of donor stars and compact objects, which is very exciting. We can also track their long-term variability. And some of those, sources within the observations that we have don't really vary that much over time. Other sources like this one are kind of strange, where my favorite data points for this are these 3 orange ones here, which were all taken 2 days apart from each other. And so it dropped by an order of magnitude over a couple of days. And so about half of them show variability on longer term timescales, but they don't vary in the same way. And at the beginning of Anna Karenina, Tolstoy started as saying, happy families are all alike and unhappy families are unhappy in their own way. And I think my version of that would be that maybe all non-variable sources are alike, but every variable source is variable in its own way. And so that's, sort of more indicators that we have, something very exciting going on here. And then in some ways, it's just the tip of the iceberg to understand them. So one other technique we can use is X-ray spectroscopy. And so this is, the number of photons at a given energy level. And we look at the shape of this and we can model this. So we have to fold in properties of the X-ray detector. And there are a few different models that we can actually use to fit this. that can tell us things about the, the physical emission mechanism of the system. So these are two of my actual spectra. I like to use these as an example because they are two sources that are close enough to each other that they show up all in the same data sets. So they're the same galaxy, the same distance. In other words, there's no observational bias to explain the differences between them, and it has to be intrinsic. So this orange one that I've overlaid this little cartoon spectrum here is best fit by a black body model that's modified for an accretion disk. So this is, sort of the thermal physics that would be given off by the accretion disk. And so it has this nice shape. And then this other source here is best fit by a power law model. So you can see that at the sort of higher energies, we have more photons where this one just sort of drops off. And so this one, might be explained by inverse Compton scattering near the central engine of the compact object. But this is a fairly phenomenological model, and it's less intuitive than the black body disk model. But there's, like one of the questions we can ask here isn't, just, can we fit them? What model can we fit them with, and what are the characteristic properties of that? One of the other questions we can ask, because we know that these things show long-term variability in X-ray luminosity, is how does the shape of the spectrum change as the source gets brighter or fainter? So, a visual way to look at this for the ones that are best fit by that black body disk model is to plot them like this. So on this axis, this is the X-ray luminosity. It may not be showing up too well, but this is 10 to the 39 ergs per second here. This is 10 to the 38 ergs per second. And then this is the characteristic spectral temperature. So it's an inner disk temperature. That's the parameter of that whole black body disk spectrum. And so this is the temperature in keV. And so you can see that we have, sources above 1 keV and then some sources below 0.5 keV. There's a little bit of a distinction here. These sources here were sort of clumpy, so they don't have the best statistics because maybe they were in shorter observations, or we didn't get enough photons, to really nail those error bars down. But we can already look for, in some of the other brighter ones, we can look for some interesting trends. And so the first one is this one that's very interesting. And so this source kind of makes sense because as that accretion disk gets hotter, it gets brighter. So a lot of galactic black holes follow this trend as well, which is, exciting to see because that's something we understand. These sources here are little weirdos because you can see, especially for this purple one, that it is very, the best fit temperature for the model was about 0.15 or 0.12 keV, and it spans a whole order of magnitude in X-ray luminosities without changing the shape of its spectrum at all. And this source, which is a bit more uncertain because it's in a completely different data set with its own issues, is also fairly similar to that one. And then they also, again, have this distinction where these ones are at lower temperatures and these are at higher temperatures. So the last question we can ask here is, how does this tie into optical emission? Because luckily I do have spectra for the three of these. So I can show you this one spectrum first. This is the one that is just the sort of, typical, nice globular cluster with, nothing going on here. So, it's sad, it would have been nice to make a connection, but we do have two spectra left. Both of these are the ones with, weird emission lines, and they both belong to these two. So, that's exciting that there's this connection. And so we can, put all of this together to try to make a very, hand-wavy global interpretation that needs more follow-up that I'll talk about in a few slides. And so, one possible interpretation is that this source could be indicative of, something like a bit more massive black holes. So that makes sense because it doesn't have optical emission or basically indicators of, weird accretion physics. And these sources, since we think that the optical emission may be linked to outflows, these can be sources, stellar mass compact objects undergoing some kind of super Eddington accretion. So there's a lot of, active, follow-up questions here. And well, the first, question is, how can we compare these better to galactic X-ray binaries that, because they're closer, we get better data, we can understand them in more detail. We also have to worry about disentangling neutron stars from the sample. So I'm going to talk about work a student of mine is doing to understand neutron stars that can reach the Eddington limit. And then also, how can we use future missions to talk about globular clusters? So for one of these, using accretion physics to try and understand the compact object, this is work that was just published by Wasundara Athukorla-Laga, who is a senior at Michigan State University. And so she did this amazing work where she compared, very global properties of the X-ray binary, the ULX, that where as the temperature increased, so did its X-ray luminosity, and she compared it to two known low mass X-ray binaries, black hole sources in our galaxy, and including GRS 1915, which is this green source here. And so she used both optical and X-ray data to sort of make these global comparisons, and she showed that her globular cluster ULX source, has a lot of similarities to GRS 1915, just an order of magnitude brighter, suggesting that if you believe a lot of the similarities, this suggests that it's a bit more massive than GRS 1915, which is a very nice result. So for understanding neutron stars, this is a new project I'm very excited about. So it's called MOOSE, Monitoring Observations of SMCX1's Excursions. SMCX1 is this neutron star X-ray binary, which can reach above its own Eddington limit. And it shares a lot of known features with ULXs that are neutron stars, including a warped accretion disk. And so we're using NICER to monitor this source so that we can understand what's going on. And one of Rowan's really, really nice results that she's working on writing up, she's a senior at McGill, by the way. And what she's found is that she's found evidence that you have this warped accretion disk where the warp of the disk is actually blocking out the neutron star and dimming it and then letting it get bright again. But this is, a very exciting project that could be a talk of its own. And then I'm sort of interested in, thinking about how we can use future missions to find more globular clusters, because, the more globular clusters we find, the more X-ray binaries we can find in them. So this is work by Emma Barbison and Jeff Wang, who graduated from McGill as undergraduates last year. And so they thought about using, this is the NGVS data set, which is going to be similar to like just a few epochs of Rubin. And so they tried to, see, is machine learning effective to identify globular clusters and separate them out from contaminants for us? And the answer is that, it worked better than I cynically thought it would, but it's clear that, there's a lot of room for improvement. And, as we look forward to Rubin coming online next year and surveying extragalactic globular clusters for us, I think that, there are good prospects for being able to use this. And I think we're sort of stuck using some kind of automated technique because Rubin Observatory is going to have so much data that the way we've been handling things is just not going to cut it anymore. So I'm going to end a little bit early here because there was a couple of slides that I pulled out last minute because I thought that the other stuff was more exciting. But sort of to summarize, it's exciting that we have 20 globular cluster ULXs that do not all behave the same. And I think we're, sort of, as we find more and more of these sources, we're going to understand what is a typical globular cluster ULX, what are the strange ones, and how can we, use their properties to understand what kind of compact objects are going on here. And specifically, can we use them to either rule in or rule out intermediate mass black holes? And, something else I'm excited that to be able to talk to Alexa about that I didn't, focus on here is what kinds of globular clusters host these. So I think it's going to be really, really exciting to, really use spectroscopy to really characterize the globular clusters, and then use stellar synthesis population modeling to pull out the actual parameters of those globular clusters, and then use something like the cluster Monte Carlo code that Claire Yee, who is a CETA fellow at Toronto, uses to try to model these extragalactic globular clusters, because in there you can actually trace the evolution of their X-ray binaries. So I think that, there's also exciting windows to understand globular cluster evolution and black hole binary evolution in globular clusters for these sources. But, sort of, I think my overall message is that star clusters are amazing and we need to find as many as they can so that, we can shake all of their secrets out of them. But I think I'll end there. Thanks.
Seem to have lost. Do I see Alexa? I don't see her on the Zoom, so perhaps she
She had to go attend a talk at
I
KAT.
see. Okay, I missed that. So in that case, let's thank our speaker. I'll take over. I thank you virtually and take questions from the group. Yeah, thank you, Tristan. If you can point it at the audience, if there are any questions there amongst the people who are there physically live.
I think for the people in the room, I think the audio connection is really bad and we can hear almost nothing.
There is a little speaker thing, but they sometimes have to walk up to it to talk to it. Right now, we can't hear anything from you in the room. Okay, while they're getting organized, let me ask a question. While they figure out their sound. So, with quasars, you have this like reverberation mapping technique where you have like time variability around the black hole, and then there's clouds further out. And looking at your optical emission lines and your X-ray, I wondered whether anything like that goes on in these types of X-ray systems.
Yeah, so that's something we really wanted to do that, but the problem is the source with the X-ray variability on those like hour-long timescales that I showed is the same one that we have all of that nice optical information for, and so it's not a straightforward connection to do reverberation mapping because of the size scale of the oxygen nebula. Information will be smoothed out on I think light year timescales. And so that means that one of the things I'm working on right now is actually pulling apart the X-ray variability to look, to basically remove the short-term trends and only look at the long-term trends so that we can make those matches. But yeah, that's something that we have, totally want to do, but it's not as straightforward as it would have been nice for it to be.
Okay. Yeah, I guess the timescales are quite different because everything's on a different scale, right, than the supermassive black holes. I mean, were you able to measure it with the current data?
Yeah.
Okay, let's try again in the room. I can see Tristan's mouth is moving, but no, we're not hearing any sound from him.
Yeah, that's what I'm going to do. I've just, oh shoot.
You can just repeat the question. You don't have to use the little Bluetooth thing.
Yeah. So whoever. Oh, it's my luck. Okay. You guys can hear us, right?
Yes. Now we can hear you.
Okay. So I guess if people have questions, just come up to the front. I know it's a bit awkward. Or just scream it. Practice your theater voice, I guess.
I guess mine is a very basic question. So in terms of so physically or theoretically, do you expect difference between X-ray emissions of black holes and stars? I mean, when the compact object is black hole versus when it's star.
Do you mean like the X-rays from like the donor star or from
from the donor star, but when the black hole, when the compact object is a black hole versus when the compact object is a star?
So like, do you mean like a regular star or a neutron star?
So I think maybe if I understand what's being asked, if you had a regular binary with two stars, is there any X-ray emission at all in those cases? I guess is the first order question. And if it does, then how would it differ then when it's?
It wouldn't be bright enough for us to see it from the distances of these things, which are typically Virgo and beyond, so 16.8 megaparsecs.
Okay. Any more questions in the room? Yeah, go for it, James.
Sorry, I missed. Did you say you were using NGVS to look for globulars?
Yeah, it was just a test, like not to find new globular clusters, because there have, the nice thing about M87 is that it's something where everybody has looked at it. So there's a paper that was published, I want to say in 2016, where they used NGVS to do photometrically selected globular clusters. Jay Strader had a survey where they did spectroscopic studies of globular clusters. And then there's also the ACS VCS survey where they used Hubble to identify globular clusters. And so what we actually did for that is we took Jay Strader's spectroscopic catalog and we matched those to the NGVS data. And then we also matched the photometrics catalogs and the Hubble catalogs to the same data sets. So they tested and trained the two different machine learning models on the NGVS counterparts to the spectroscopically selected sample. And so when they did the test and the training, how you're supposed to, the model said, I am 98% accurate at selecting globular clusters. And I'm very skeptical of machine learning algorithms. So then we tested that additionally on the two other methods of selecting globular clusters, both using Hubble and the photometry selected ones, but again, all in the same data set. And they were like way less accurate than the 98% accuracy level that the algorithm suggested.
This is just using the 5-band optical data.
And the full with half max.
Yeah, because no, I mean, what I was thinking of was, there were a couple of papers showing that if you use the K-band, it's much, much easier. Which obviously limits you a little bit because you don't have that imaging necessarily on systems.
Yeah.
So I mean, it's pretty easy to know which ones are globulars once you have the K-band in there, basically.
Yeah, but what is that going to look like with LSST data? And so I think that's something where if we can combine like Roman or Euclid with LSST data, it's going to be a lot more powerful. But at the end of the day, it's just like there is going to be so much data that we have to figure out how we're going to sift through it to find the things we care about.
How far into, I mean, what's the longest wavelength again for LSST?
It's UGRAYZ.
Okay. Yeah. Okay, thanks.
Yeah, so I mean, that was the nice thing about the NGVS survey is that it's exactly Rubin data.
Any more questions in the room? Okay, I mean, I kind of have one about the machine learning your students were doing. So
yeah,
I'm kind of curious, what sort of model specifically were you using? Were you using like non-negative matrix factorization or something a bit deeper than that? And I know you said you got 98%, so I'm kind of curious as to what sort of architecture you're using, because it sounds like you were sort of fitting different spectra and trying to identify.
No. It's nothing that complicated. So one student did a random forest algorithm, the other did a neural network. But basically the philosophy here was, let's pretend that we have Rubin data and we can only plug in full with half maxes and can only plug in in each of the 5 filters what the photometry is. And so we use the spectroscopic data set as like, these are the bona fide globular clusters. And then they plugged the photometric properties in that corresponded to, the same RAN deck as the spectroscopically selected clusters to actually do the testing and training of the models.
Okay, very interesting. I see Mike.
Yeah, I will ask my own follow-up question. So on that topic, when you said when you tested on real data, it wasn't really 98%, it was less than that. But I assume then the contamination is what then? Is it coming just from stars that are point source like, that have similar colors, or on what objects is it failing?
So this was the funny thing. So the original models, and there's some philosophical debates about this, but we said that the ideal algorithm would be able to, reject background galaxies and foreground stars, and potentially separate out ultra compact dwarfs from globular clusters. And of course, the philosophical debate here is, do you think that ultra-compact dwarfs are different things than globular clusters? Which is not a conversation I want to have right now. So we just focus on the globular clusters because there's not that many, UCDs if, that's your cup of tea or not. And so for within the test and training sample, it was accurate. And then when we pulled it on a larger sample of things, so it was actually kind of funny that the two methods flip-flopped. And so there was one method that when you fed it in only Hubble selected clusters, it actually did a great job reselecting the Hubble selected clusters. And when you fed it in the photometrically ground-based selected clusters, it was like 50% accurate for those. And then the other model was the exact opposite, where it did a great job reselecting the photometric clusters, but it did terrible at reselecting the Hubble clusters. And I think there was a couple of issues here. And so one is, in the case of the Hubble selected clusters, this was a much smaller sample because Hubble has a smaller field of view. And that wasn't a sample where we had a list where we only had a list of clusters for those. And I think the model was expecting that there should be contaminants when like most of the stuff was a cluster and the other, whatever. So I think that was like one issue with the Hubble thing. And then for the photometrically selected clusters, I'm not sure like why the one method flip-flopped, but that one was like, a bigger sample, and it had in there, it had things that were rejected as being stars or rejected as being background galaxies. So yeah, it was like gratifying that it worked better than I thought it would, but it also made me realize you can't just like, spend 2 weeks on, Google School of Code learning how to do a neural network and then, apply it wildly to everything. But that's definitely something I want to follow up on more in the future, because I think it's, something that we have to do.
Well, fair enough. If you want to look at more, UGRIZ data, there's the Union Survey, which you're to join since you're a Canadian at the moment.
Cool.
Okay. Any other questions in the room or online?
Looks like we've exhausted all the questions in the room.
Okay, well,
I think the smell of pizza is starting to walk.
Smell of pizza. All right. Too bad you. Yeah, okay. Pizza actually, but I'm at home right now. Okay, so let's thank Kristen again. Like, you're not getting much audio, but you can at least see people clap.
Yeah. All right, I'm just gonna stop the recording.
Okay, thank you. So will I. Thanks, Kristen.